We're Team 6. My name is Guerrero.
My name is Daniel Castellanos.
And my name is Jose Gomez.
And we're doing our project on lower limb prosthetics for children. Thank you.
I'm going to take you through our problem statement. Children until the age of 15 on average outgrow their prosthetics on a yearly basis, making them extremely expensive on their own. They're also, of course, average $5,000 to $15,000, so of course, it's a lot of money throughout the years. This picture is a perfect example of a little girl. You can tell she's very young, and she's already gone through 5 prosthetics. Our resolutions are to make the prosthetic affordable, adjustable, and attainable. And our global design elements, we want to make the prosthetic as affordable as possible all over the world, especially in developing countries, which of course will be beneficial in the United States and in developing countries. By using common mechanisms and materials, attainability will be maximized all over the world. Our goals, we want to design a above-knee amputation prosthetic that is affordable, adjustable, and safe as possible. We want to manufacture using mostly 3D printing and purchase parts, and we want to help a lot of children in need and test the prosthetic in as many real-world situations as we can. Literature survey, 75% of amputations are lower extremity, which is why we decided to go with the lower leg amputation. Children amputees go through a lot of emotional and self-esteem issues with it. It's another thing we wanted to help them with. As you can see here, we're trying to make prosthetics as little expensive as possible. Real-world situations tested by the AOPP, level walking at a self-selected comfortable velocity, stopping abruptly, sidestepping abruptly, stepping onto an obstacle, and interruption of knee extension during swim phase, as if an obstacle or a person were to stop as the prosthetic as the knee extends. FDA regulations. Prosthetics are generally categorized as a class 1, making them they're associated with low to moderate risks and are therefore exempt from pre-market review. And they do, however, require medical device listings, and there are a lot of labeling standards and registrations that are going involved if you actually want to test the prosthetic out on children. Okay, Crystal's going to take us through our alternate designs.
Thank you. So for our alternate designs, we want to make it an adjustable prosthetic for children between the ages of 5 and 12. And we want to try to make the prosthetic as adjustable as possible and to keep it as affordable as possible. And for our first design, we're going to do an alternate designs for the shaft. First, we want to do a pin-based system for the shaft, a threaded-like system for the shaft, and also a clamp-based system for the shaft. In the next slide, we'll go in detail in our first alternate design. We are planning to have 2 components in the shaft. One part of the shaft is going to have the various levels, so the holes in the calf portion, and the second part is going to also have holes. And as the shafts come into place, a pin could be inserted to keep the prosthetic in place. And for our second alternate design, we'll have a threaded-like system that will increase stability and will also be a 2-part component, and it'll be similar to a thread and a threaded bolt system. And for our third design, we'll have the clamping system, and it's also going to be a 2-part component, and it will be able to adjust as the child grows, and it will be able to clamp in place. And for our foot design, we also want to make that adjustable as well as the child grows. And we're thinking about having a pin-based planetary extension, a threaded planetary extension, and a slider notch extension. So for our first design, it's also going to be a 2-part system, similar to our design alternative 1 for the shaft. So one part is going to have several different levels, and the second part is just going to have one level, one set of holes, so it can match up with the second part the prosthetic, and a separate pin will be placed so it can keep the prosthetic in place. And for the second design, we'll have a threaded system that will also be similar to our shaft design too. And for our third design, we'll have a slider notch system. So kind of like the scooter shaft, steering shaft. So one part is gonna have the various levels of holes, and the second part is gonna have the pins based on a spring-based pin system. So as you squeeze it, it can be adjusted and be able to adjust with the child within time. And Daniel's going to talk about our socket design.
So for our socket design, we need to incorporate the residual limb to fit the growing child. We're going to be using mostly plastics will be utilized for the residual limb to secure it in place. We want to make it a little bit, as you see in this example, a little bit aerated so it avoids sweating and makes it more comfortable for the child as they grow. We will be using for comfort as well, trying to incorporate different types of memory foams or silicones for the socket. So it'll be a little bit more comfortable for the child as they grow. For moving on to the knee, the knee we will be using will allow the child to move their limb. We're trying to use either a 4-bar mechanism or a spring-based system to allow the child a little bit of ease of use as they extend their knee or bring it back. It will have a feature that allows it to be tightened. So as the spring or the child grows, they need a little more force or a little more help. The spring can be adjusted to help the child with as they grow. The target cost is under $1,000. Ideally, it will be less, but that will be for our design and what design we actually choose. By using low-cost materials and a simplistic design, and to make it easily manufacturable for wide use of wide range of use. We will be using we're considering using different materials such as 3D printing, aluminum steels, and high-density polyurethane plastics for our design. Our timeline, we have selected our project. The research has gone into it. We have researched what we needed to do and what it goes into building or making a prosthetic, especially for such a forgotten age range such as a child. And we have design in mind for alternatives. So we have a few designs to choose from. We're trying to see which one works best to further make our prototype or make ourselves something that we can physically show. We will be starting to model the project in SolidWorks or other programs and begin simulation analysis within the program to determine the stresses involved within the prosthetics. In conclusion, basically what I stated, the research has been done. We will be expanding to our initial design and planning stages. And we'll hopefully in the future, by next semester, we'll be able to produce a product, something that shows that we have tested and made our final design for a growing child.
Thank you.
Thank you.
Any questions?
Questions?
Looking at your design using metals and composites, are you certain you can manufacture a prosthetic like for under $1,000 when the usual like ranges from $5,000 to $50,000?
We believe so. We have researched different materials and different manufacturing processes to develop it. It might not be top-notch for the prototype, but I believe it is achievable.
And since we're trying to keep the design as simple as possible, so we can keep the cost as low as possible, not adding electrical components or any motors into our prosthetic.
My second question is about the joint. What range of mobility will it allow the person wearing it? Is it 90 degrees? Is it full mobility as a regular leg?
We want to achieve a 90-degree angle so they can extend, bend it so they can sit down with the knee, and that's our objective. Our main goal is to make it as functional as possible, like a regular human's foot or knee.
Yeah, we've concentrated on making it as adjustable as possible, and in the shaft portion and in the foot portion of the prosthetic.
Have you considered the mechanism that will prevent the leg from, when it's fully extended, to buckle when the person is walking?
That's a part of our idea. The spring's got to be strong enough so the person can stand up straight, that without buckling to the side.
But while he's walking, when he extends the leg, what makes sure that the leg is fully extended so when he takes the next step, it doesn't, the knee doesn't bend?
Again, the spring would have to be tight enough. It'll extend out all the way. We've got to design it so to make sure it extends out all the way. So when he steps,
It'll like
Stays.
retract the spring.
Yeah,
will
there'll be a
retract.
stop. There'll be a stop, and it'll be strong enough to, or the movement will be determined that it will lock in place before he takes the next step.
which is part of the time, because again, as the kid grows and gains weight, it's going to take more for that to extend out and to handle the pressure of him just standing or walking.
Any other questions?
Yeah. When I look at the design, there's three areas that are big concerns to me. One's the knee, one's the ankle, and one is the adjustability. The question I ask right off the bat is there any open source work out there that you might be able to eliminate one or two of those, that you could
Yes.
work on the third one?
We have found knees and ankles that are open sourced for designs that are very simple that have been used. So one uses a 4-bar system for the knee that addresses the issue regarding the locking it. It has the motion that it can extend back and forward as the person takes a step.
So my guidance to you is just to restate your problem statement. Take the open source into that joint and do your work on the other.
Okay.
And make sure you do a really, really good job of it. And simulations and off-incident stuff, and the comment about off-angle is exactly right. I mean, the biomechanics piece of this puzzle is not simple.
Yeah.
And I know, for example, from biomechanics course I took, that your ankle sees 9 times your body weight on a standard step. So you gotta make sure that you design it right so that the children don't get hurt with this.
Exactly.
That's my guidance.
Thank you.
Have you contacted anybody at like an orthopedic surgeon that specializes in kids or Miami Children's to see if there's somebody there that when you get, like Chip says, gets further down the line a little bit, would say, yeah, that'll work, or you might want to look at something a bit different? It seems like somebody in the expert could really help you.
We haven't seen the physicians and stuff like that, but
we have
looked
researched
for
different companies that,
different companies.
yeah, there's actually some companies that do work with FIU that we're trying to get in contact with so they can advise us on this project.
I think that would be helpful.
Yeah, definitely.
I mean, I'm an engineer that has to do with gears. I know nothing about legs, so.
Yeah, being a mechanical student, you find that. Anything else? Thank you.